Hi students, as you can see in this picture we have the aurora borealis or the northern lights, and displays like this one are caused by cosmic ray particles trapped in the Earth's magnetic field. So when these particles collide with atoms in the atmosphere, they cause the atoms to emit visible light. Our next section has a lot to do with this Earth's magnetic field, and it's on magnetism. And in terms of applications, magnetism is one of the most important fields in physics. Large electromagnetics are used to pick up heavy loads. Magnets are used in such devices as meters and motors and loudspeakers. Magnetic tapes and discs are used in sound and video recording equipment and to store important computer data. Intense magnetic fields are used in magnetic resonance imaging. Many of you may have had an MRI before, which explores the human body with better resolution. And let's say there are great superconducting magnets that are used in cyclotrons that guide particles into targets. I'm sure you have all heard of the Big Hadron Collider. And at nearly the speed of light, these particles are accelerated due to magnets. Rail guns, if you know what a rail gun is, used in magnetic forces to fire high-speed projectiles, and magnetic bottles hold antimatter. And possible key to future space propulsion systems may be found in the study of magnetism. So why magnetism now? Well, magnetism is very closely linked with electricity, and magnetic fields affect moving charges, and moving charges are going to produce magnetic fields. So changing magnetic fields can even create electrical fields, and this phenomenon signify an underlying unity of electricity and magnetism, which a guy named James Clerk Maxwell first described in the 19th century. So the ultimate source of any magnetic field is an electrical current. So let's look at our objectives. What is it that we're actually out to accomplish? Okay, to begin, you can just look up and see that these are the first three things that I would like you to be able to do, and that's discuss the basic properties of magnets and magnetic fields, and make sure you can contrast the magnetic fields and properties of magnets with electric charges, electrical fields. 2, characterize magnetic materials as hard or soft. This is just whether it's a permanent magnet or a temporary magnet. And 3, identify the origin of magnetic fields and moving electrical charges. And let's state some applications of magnets in their fields. Permanent magnets have long been used in navigational compasses, and as you can see in this picture, this illustrates a compass needle, and it's a permanent magnet supported so it can rotate on a little pin. And when the compass is placed on a horizontal surface, the needle rotates until one end points approximately north. The end of the needle that points north is labeled the north magnetic pole, and the opposite end is labeled the south magnetic pole. And what may seem a little strange is that the north pole of a compass points to the Earth's geographic north. So going this way is geographic north. Okay, and the south pole points to geographic south. Now, geographic north is also known as magnetic south. Now that seems a little confusing, right? So where Santa lives on the North Pole is actually geographic north, but it is magnetic south. And where the penguins live is actually geographic south, but magnetic north. So this is pointing to magnetic, so we'll put mag north. Okay, and there's a reason for this. The reason behind this is because like poles repel each other and unlike poles will attract each other. So the north end of a magnet will be attracted to the south magnetic end of the Earth. So geographically, the North Pole is magnetically a south pole. And I know that seems to be a little confusing. Now, this behavior is similar to that of unlike electrical charges. However, there's a big difference between magnetic poles and electrical charges. For example, it's possible to have separate positive and negative charges and produce isolated charges. As I mentioned, you can separate the positive and negative charges, but you can never separate a north and a south pole. There has never, ever been found a magnetic monopole. We call it a monopole. No such thing. Okay, that would be one single pole, a north or a south pole. And any attempt to separate the north pole and the south pole by cutting a bar magnet in half fails, because each little piece of the magnet becomes its own little north and south pole. Okay, just as a smaller magnet. Now, surrounding a magnet, there's going to be a magnetic field. And as you see here drawn on the magnet, we have a magnet with a north and a south pole. And what we know is that the magnetic field originates from the North Pole and circles around to the South Pole, but it goes through the magnet to make a complete closed loop. So it goes in this direction, or from here we can go in this direction, and again going through the magnet to form a closed loop. Okay. So where on electrical charges, the electrical field could go out into infinity. On a magnet, the magnetic field forms closed loops all the way around, originates from the north, and terminates at the south. So going from north all the way around into the South Pole. Okay. So here's a much better picture of a magnetic field surrounding a magnet. And the magnetic field is analogous to electrical field that it exists in a space around electrical charges. And like the electrical field, the magnetic field can be represented by lines of force. Okay, it has both magnitude and direction. But the direction of this magnetic field at any point in space is the direction indicated by the north pole of a small compass needle at that point. So in other words, if each one of these little arrows represented a compass, you would see that the compass always points toward the magnetic south, okay, and away from the magnetic north. Okay, so the north pole of the compass, I'm going to draw a little north here, the north pole of the compass always points in the direction of the field. And I want you to take note too that the magnetic field is always, the magnetic field lines are always tangent to the magnetic field. So you can see that each one of these lines is tangent to a field at that point, just much like we talked about with electrical fields. So the compass, this would be, each one of these arrows would represent the compass as pointing in the direction of the magnetic field. This drawing also shows how compasses can be used to map out the magnetic field in space around a bar magnet. And since like poles repel and unlike poles attract, the needle of each compass becomes aligned relative to the magnet in the manner shown in the picture that I'm going to place. As you may remember, when we placed an electrical charge in an electrical field, it exerted a force, or there was a force exerted on that field. And if you remember, this was the field, the E, and this was the little charge placed in the field, and this was the force felt by the charge. So when a charge is placed in an electrical field, it experiences a force. Now, when charges are placed in magnetic fields, it also experiences a force. But there are certain conditions that must be met that are a little bit different than those in a magnetic field. So what are the conditions? Well, there are two. One is the charge must be moving because no magnetic force acts on a stationary charge. So in order for the charge to experience a force, the particle must be in motion. And two is the velocity of that moving charge must have a component that is perpendicular to the magnetic field. In other words, if I draw the magnetic field like this, going left to right, okay, this charge must be changing lanes like this, okay? Or we could also do this. As long as it's changing lanes, in both of those cases, the charge will experience a force. Now, if the charge is not, if it's moving parallel as like that or anti-parallel like that, no force. Okay, and the reason is because there's no component perpendicular to the magnetic field. And the way I like to remember that is you just see that the charge must be changing lanes. So for our charge to have encounter a force, okay, you must have a charge. Okay, the charge must be moving. Okay, and the velocity of the charge must be perpendicular to some component of the magnetic field. Now, the letter B represents magnetic field. Okay, so if you have a charge, it's moving, and some component of that movement is perpendicular to the field, then the particle will experience a force. So above, this is how the magnetic field B is defined. The magnetic field B is defined at any point in space as the force per unit charge times the velocity times sine theta, where F is the magnitude of the magnetic force on a test charge, and we're going to call the test charge QO. In the magnetic in the magnitude of the test charge is V is the magnitude of the velocity, which makes the angle theta with the direction of the magnetic field. So the magnetic field is a vector, and you can determine the direction by using a small little compass needle. Now this one is a little bit more complicated. What are the units for magnetic field? So the SI units for magnetic field, okay, we have force, which is newtons, over charge, which is coulombs, times velocity, which is meters per second. So if we simplify that a little bit, you get Newton seconds per coulomb meter. Newton seconds per coulomb meter. Now that's pretty complex, so we give it its own name, and we'll call it a Tesla. That's 1 Tesla. Okay, or 1 T. So that is the unit. The Tesla is the unit of the magnetic field. And this unit of magnetic strength that follows from that equation, okay, the Tesla, we contribute to a Croatian-born American engineer named Nikola Tesla. So it's the strength of the magnetic field and a unit test charge traveling perpendicular to the magnetic field at a speed of 1 meter per second.